Imagine a spacecraft arriving at Mars faster than a rifle bullet, aimed at a thin red atmosphere that is both rescue system and threat. For months, the trip has looked quiet from the outside. Then the clock compresses into a few violent minutes. The heat shield faces plasma. A parachute has to open while the vehicle is still supersonic. Radar has to find the ground through dust and motion. Engines have to light at exactly the right time. And Earth cannot grab a joystick to save it. By the time a clean signal reaches mission control, the answer has already happened on Mars. This is Path to Mars on the Quantum Files. Episode 2 is about 7 minutes of terror, the landing problem that turns every Mars dream into a real engineering test. Before anyone talks about boot prints or habitats, the planet asks one blunt question. Can you arrive in one piece? Landing on Earth is hard, but Earth gives you thick air, long runways, oceans, and rescue teams. Landing on the Moon is hard in a different way, because there is almost no atmosphere, so you know from the start that engines must do the stopping. Mars sits in the awkward middle. It has enough atmosphere to create fierce heating during entry, but not enough to slow a heavy spacecraft gently. That means engineers cannot choose one simple trick. They build a chain. A heat shield absorbs the first punishment. A parachute or drag device removes more speed. Guidance keeps the craft pointed toward a safe target. Rockets finish the job. For the Curiosity and Perseverance rovers, a descent stage lowered the rover on cables so the engines would not blast the science vehicle directly into the ground. It looked theatrical, but it was practical. Mars landing is not a stunt. It is a handoff race where every runner is moving too fast and nobody gets a second baton. The Martian atmosphere is mostly carbon dioxide, and at the surface it is usually less than 1% as dense as Earth's. That thinness is why a person cannot breathe it and why a parachute has such a difficult job. But during entry, when a spacecraft is moving at interplanetary speed, even thin air matters. The vehicle compresses gas in front of it, heating the flow until the outside becomes a blazing shield of energy. Some of that heat can be useful because it turns speed into atmosphere and shock. Too much of it can destroy the vehicle. Later in descent, the problem flips. The craft is lower and slower, but still far too fast for a gentle touchdown. The atmosphere has spent its best trick and the lander still needs help. That is the Mars paradox in plain language. There is just enough air to burn you on the way in, and not enough air to catch you at the end. In 2021, Perseverance gave the public the clearest view yet of what a modern Mars landing actually does. The cameras showed the parachute opening above Jezero crater, the heat shield falling away, the ground rushing upward, the descent stage hovering, and the rover settling onto its wheels. It was beautiful footage, but the beauty can hide the discipline underneath. The mission had to sense where it was, compare the terrain to onboard maps, avoid hazardous ground, and complete the sequence without a live pilot. Perseverance also carried ingenuity. The small helicopter that later proved powered flight could happen in the thin Martian air. That was a bonus lesson after landing, not a rescue option during it. The landing itself was still a one-time performance. Rovers have shown that complicated automated choreography can work on Mars. Human-scale landers will ask for the same choreography with much larger mass and far less tolerance for failure. Older missions aimed at large landing ellipses because small errors in navigation, atmosphere, and winds can grow during descent. Modern missions are getting better at tightening that uncertainty. Terrain relative navigation lets a lander look at the surface, compare what it sees to stored maps, and adjust its path away from the worst hazards. That matters because Mars is not a clean landing pad. It has rocks, slopes, dunes, craters, dust deposits, and ground that may look calm from orbit but punish a landing leg. The final decisions have to happen locally. Earth can send commands before entry and receive signals after the fact, but it cannot steer around a boulder in real time. For crewed missions, autonomy will not be optional decoration. It will be part of the safety system. The crew may understand what the vehicle is trying to do, but during the fastest moments, the lander itself has to think and act within its tested limits. A rover around the mass of a small car is difficult enough. A crewed lander, a pressurized habitat, a nuclear power unit, or a fuel plant pushes the problem into a different class. Mars air does not become thicker because the payload is more important. Bigger payloads need more drag, more engine performance, more stable control, or a new entry shape that spreads heating and force across a larger system. NASA and industry studies often discuss technologies such as supersonic retropropulsion, where rockets fire while the vehicle is still moving fast through the atmosphere. That idea has been studied and partly demonstrated in Earth tests and launch vehicle landings. But Mars-scale crew landers still demand careful proof. Another option is a campaign of multiple smaller landers that pre-position cargo before the crew launches. That may sound less dramatic than one giant arrival, but exploration usually rewards logistics. If you cannot land the heavy pieces safely, you do not have a base. You have a drawing of one. The uncomfortable truth is that you cannot fully rehearse a Mars entry, descent, and landing on Earth. Engineers can test heat shield materials in arc jets, parachutes in high-altitude campaigns, engines on stands, guidance software in simulation, and full vehicles in carefully designed partial trials. They can learn from every previous Mars success and failure. But the exact combination of Martian air, gravity, dust, terrain, and interplanetary speed only happens at Mars. That is why margins matter. Redundant sensors matter. Conservative landing sites matter, especially early. The phrase 7 minutes of terror is catchy, but the real work is years of quiet terror before launch. When teams ask what happens if a sensor reads wrong, a parachute tears, an engine underperforms, or the ground is softer than expected, the goal is not to imagine every nightmare for drama. The goal is to make the vehicle boringly capable when Mars stops being theory. Cargo can be lost painfully and expensively while the program learns. A crew cannot be treated that way. Human landers need a different level of fault tolerance because failure cannot simply mean another crater on the map. Abort options are harder at Mars than at the Moon. Once a lander is committed to entry, there may be no easy path back to orbit if the sequence breaks late. That reality pushes mission designers toward pre-landed assets, strong weather forecasting, tested landing zones, and vehicles that can survive off-nominal events without demanding miracles. It also argues for robotic cargo missions before the crew, not as a lack of courage, but as proof of the runway. Optimistic realism means celebrating the skill that has already landed rovers while admitting that people add stakes, mass, and ethical weight. Mars can be reached. The first arrival with humans has to be earned before the clock starts. That means treating every cargo landing before it as data, not ceremony, and letting the planet teach engineers where confidence is deserved. When a heavy lander reaches Mars safely, the mission changes from animation to inventory. Power systems can unfold. Habitats can be checked. Rovers can scout. A fuel plant can start the long job of turning Martian resources into return capability. But every one of those later wins depends on the first minutes working exactly well enough. That is why landing sits so early in the path to Mars. It is not the glamorous ending of the trip. It is the doorway that decides whether the rest of the plan gets to exist on the surface. Next time, we follow one of the most important things a landed system can do: make fuel on Mars.